Hello everyone, I'm Zhihao Wang from the Computational Marine Hydrodynamics Lab from SJTU, and my presentation is about numerical study on slamming laws of ship advancing in a focused wave. My presentation is divided into 5 parts, and let me start from the background. Ships in the marine environment often interact with the waves between the damping action, and the hull will be subjected to great damping pressure. Huge instantaneous damp loads may directly damage the outer hull plate, causing the ship to take on water or even sink. So, in the past, many experiments have been done to investigate the slamming loads of the ship. So far, experimental tests is the main approach to investigate the performance of the ship's slamming loads. Instruments like high-resolution camera, wave evaluation measurements with wave probes, etc. And here is a photo of an experiment on the extreme bow flare slimy loads of 10,000 TEU container ship carried by Kim. Though experiment is a major way to investigate this, CFD is becoming a powerful tool to seize the details of the flow information. With development of computer technology, the computational efficiency of computational fluid dynamic methods has been greatly improved and widely used in many engineering fields. On the right is a picture about ship advancing in freaking waves carried by Liu. And the second part is the numerical method. For all the simulation, the Noiform SJTU server is applied. It's the open source toolkit combined with the 6 degree of freedom motion, numerical wave tank, and the mooring system. For the free surface capturing, we are using the Wolf method with artificial compression technique. The red circle shows the artificial compression, and the equation is the transport equation. In this equation, UR is the velocity field used to compress the interface, which can give a sharp prediction of the interface. And the waves to form is light for numerical wave tank. It's using an explicit relaxation method. In this equation, phi is the velocity of fluid or the volume fraction, and omega r is the relaxation factor between 0 and 1. Right there, the picture simplifies how the waves to form gives us a numerical wave tank. It has a wave maker relaxation zone and a wave damping relaxation zone. In these relaxation zones, it starts from an objective solution and evolves into the numerical solution. Waves to form provides 3 options of relaxation factors. The right picture shows the results of these different equations. And the equation 1 is the default option as the relaxation factor in waves to form, and P takes a value of 3.5. I'm using the dynamic overset mesh for applying for large-scale motion, background mesh for stream field, and the submesh for moving objects. Third part is the geometry and the conditions. The numerical simulation is using the KCS shape model with 1 to 85.2 downsizing ratio. And the parameters of this shape is shown in this tablet. Grid is generated by BlockMesh and the SnappyHexMesh tool in OpenFOAM. In several essential refinement regions are used to better resolve the slamming phenomenon, and the total grid number is about 3.99 million. This picture shows the computational domain of this case. The dimensions of the computational domain are set as follows. In x-axis, it's about 4.5 L, and in y direction, it's about 2 L. In z direction, it's 3 L. A wavemaker relaxation zone with a length of 0.5 L is set as the inlet of the computational domain, and the wave damping relaxation zone is 1.5 L. In the simulation condition, the wave is focusing on 3 different positions of the ship: on the bow of the ship, the midship, and the stern of the ship. And I put 25 probes to calculate the slamming pressure of the ship. The third part is the results and the discussion. The generation of the focused waves is independent of the significant wave height. As the amplitude of the frequent wave increases, spectral peak frequency needs to decrease accordingly. Otherwise, the wave breaks up when the wave is focused, and thus the desired amplitude cannot be achieved. In this study, the spectral peak frequency is set as 0.54 Hz, and the corresponding spectral peak wavelength is about 2 times the length of the ship. And there will be 10 degrees in a wave amplitude and 200 degrees in a wave length. And this is a wave generation validation of the waves to form compared with the theory. From this picture, you can see the error of the maximum wave amplitude is not more than 2%, and the error of the focusing moment is not more than 1%. The main features of the focused wave are preserved. In the first peak and the truth, before the maximum wave peak will be higher than the theoretical solution. The focusing moment of the maximum wave peak will be earlier than the theoretical solution, and the first true after the maximum wave peak will be higher than the theoretical solution, which leads to the numerical solution being asymmetric about the focusing moment. This phenomenon may be due to the larger wave steepness of the maximum peak and the enhanced interference among the subwaves, which in turn cause the CFD results lower than the theory. And this is the case A. The wave is focusing on the bow of the ship. The upper picture shows the moment of the wave focusing. It's a pressure counter of the ship, and the lower picture shows the moment of peak slamming. And this is when the wave is focusing on the midship of the ship. This is when the wave focusing on the stern. In every condition, the ship is in the bow bearing condition when the peak slamming pressure appears. For case A and case B, the ball is in a trough before the focused wave, and the ship is in a bow tilt state. When the wave focuses, the wave lifts the hull and starts the stern inclination. When the waves move to the stern of the ship, the ball enters the water and generates violent thumping, and the maximum pressure occurs in the time period when the ball enters the water after the wave focuses. And for case C, the maximum slamming pressure occurs before the wave focuses. The ship's bow is tilted to contact with the next wave valley and generates severe stamping phenomena. And this picture shows the time history of the pressure on the bow of the ship. And the right picture is a spectral of this pressure time history. The low frequency wave plays a major role in the damping pressure. And the last part is the conclusion and future work. Despite the position wave focuses, the peak pressure always occurs on the bow of the ship, and the ship is in a bow-bearing condition, either before or after the wave is focusing. The low frequency waves plays a major role in the slamming pressure, and when the wave is focusing on the midship, a second peak appears in the spectral, which is more intense and with higher frequency. For future work, it will focus on the elastic hull, which will be deformed and the action of the huge slamming force. In this study, only slamming loads under extreme sea state is studied for irregular waves, which is a short-time analysis and the study of probabilistic characteristics of the slamming loads in irregular waves is of greater value for practical engineering application. And only slamming received by the hull under head-on wave conditions is considered. The response of hull under focused waves under oblique wave condition will be investigated in the future. Thank you for your attention.
Thank you. Questions, please?
Thank you very much for your presentation. Can you go back to the slide of your wave validation part? So I want to say of your input wave. Yeah, I can go back another top one. Yeah, so I'm also doing focused wave, and I know focused wave is you choose lots of wave components and focus them at the same position, focus time. So I wonder why you choose this peak frequency. Did you use any wave spectrum to create those?
It's a Jones warp spectrum. Yeah, and the frequency is. I've done a lot of frequencies, and this frequency shows a better results. Other frequency may cause the wave break.
Okay, so you want to make sure your wave is not breaking.
Yeah.
Have you checked your input focus position and your output, the actual break? Focus position. Is that consistent or not?
I haven't done this. Yeah.
I think maybe we can discuss later because I found it's quite interesting of the input and output.
Okay.
Thank you.
Thanks for your question.
Thank you very much. Any more questions? Okay, so while you're here, go ahead.
Thank you for the presentation. A small question. Since I don't do the retraction, so I want to know why you choose the relaxation zone to generate waves rather than the wave maker on the piston type or something else.
It's the waves to form this. This tool requires a relaxation zone to generate the wave.
relaxation zone is more appropriate for focused wave.
Sorry, I didn't.
Sorry for that, and you mean you chose the relaxation zone because you can get the right focus wave pace?
Yeah, in waves to form, you have to put a relaxation zone to get the correct wave.
Or it's going to the zone?
Yeah.
Perhaps I can help here if you allow me. Okay. So there are codes like, for example, Fine Marine, which will use a wave generator to create the wave. And the problem with that is that you have to have quite a long period for the wave generator to create focused wave through motion. And then we have to follow that wave until it comes to the ship. What the relaxation zones do is they will calculate the analytical shape of a focused wave at a point in time, and that will be imposed onto the solution. Okay, so you have two benefits. The first one is that the precision of the shape of the wave is much better, and the second is you don't have to have the CFD simulation of the wave tank in order for the focused wave to develop from the motion of the body. Okay. So in CFD, we mostly use wave relaxation techniques because they are compatible with the way that the simulation is done. Okay. Does that answer your question? It is possible to do it, and I have done it, but you have to be very careful with the motion, because the motion of the wave maker, as you probably know, needs to be very precise. And we have issues with mesh deformation, time step size, and the actual effect of the pressure. Okay, so it is possible, but the simulation would be maybe 3 or 5 times more expensive. Okay, may I ask some questions, please? Okay, so can you go to your previous slide, please? No, next one, sorry. Next. I want the one with the wave shape when you compare the analytical and the numerical shape. That one. Okay. Now, for the people who don't do waves, this looks good. Okay, but in fact, this is not a great result. The reason for that is that you only have about 10 cells across the height of the wave from peak to peak to throw. In my experience, you need about 30. Okay. And with the rest of the settings using Crank-Nicholson discretization in time, your error here should be at least 1 0 better. Okay. So the maximum error in amplitude should be less than 0.1%. Okay. So the question that I have is, do you have any experimental data to compare with for this simulation?
No.
Okay. Do you know any experimental data? No?
No, yeah.
Okay. Now, the second question that I have is, when you create a focused wave like this, you will have a wave packet. Okay, so how many components do you have in the wave packet? And what form of wave do you use?
60.
60.
Yeah.
That's good. And are they fifth order Stokes waves, or are they better than that?
Fit to the Jones slope.
Okay. But what wave shape are you using? Stokes 1, Stokes 5, stream function wave?
Stokes 5.
Stokes 5. Okay. So one of the issues, the last question that I have is, does your ship have forward speed?
Yeah.
Okay. So if you use Stokes 5 waves in forward speed, you're going to have the superposition of those waves. And that will also cause you the phase error that you have here. Okay, so in my experience, it would be better to use stream function waves to do the focusing. And that is going to give you a better position of the wave.
Thank you.
Are there any more questions, please? In that case, can we thank the speaker for a very interesting presentation?